Here's the thing with rational functions. They have something that we have not yet worked with. They have asymptotes. A-S-Y-M-P-T-O-T-E-S. Has anybody ever heard of an asymptote? No. Okay. Asymptotes are like those dotted lines that a graph gets closer and closer and closer to, but never crosses. So you'd put them on your graph, and the parent graph has one on the y-axis and one on the x-axis. So the original equations are y equals 0, that's the x-axis, and x equals 0, that's the y-axis. What happens if I plug in an x-coordinate of 1? What's my output? 1 over 1 would be 1. So I plug in an x of 1, I get a y of 1. What happens if I plug in an x of 2? What's 1 over 2? 1/2. If I plug in an x of 3, what's 1 over 3? 1/3, and then 1/4, and then 1/5, and so on. Does everyone see why that will never reach 0? Even if I plug in 100, it'll be 1/100th, so it'll be like infinitely close to the x-axis, but it won't actually ever touch it. And that's sort of what an asymptote does. Now, we plugged in a whole number 1. What if we plugged in a half? What's 1 divided by a half? What? How many times does a half go into a full? Twice. So if I plug in a half, I get 2. If I plug in 1/3, what's 1 divided by 1/3? How many times does 1/3 go into one whole? 3. And so likewise, even if I plug in like 1/100th, the answer will be 100, and this kind of shoots up towards infinity. And so what you get with these rational graphs is like these curves that are sort of nestled in corners of these corners are created by the asymptotes. We have an asymptote, this vertical one anyway, because that's an x-coordinate of 0. And if I plug in 0, what's 1 divided by 0? Undefined. So that vertical asymptote kind of blocks that out. You cannot have a point on a vertical asymptote. Okay? So if we jump to the other side, what if I plug in -1? What's 1 divided by -1? -1. So we have the point -1, -1. What if I plug in -2? What's 1 divided by -2? -1/2. And then I'll plug in -3, and it'll be -1/3 and -1/4. So it gets infinitely closer to that x-axis again. And then if I were to plug in -1/2, if 1/2 goes into 1 2 times, then -1/2 goes into 1 -2 times. And so on. And even if we were to plug in -1/100th, that goes into 1 -100 times. So that's your parent graph. Really, the critical points that you're going to have to focus on, like shifting and so forth and reflecting, that'll kind of be the basis for the rest of your graph, are 1, 1 and -1, -1. So if you shift everything to the right, between your asymptotes shifting and those 1, 1 and -1, -1 shifting, you'd get your critical points. Okay? So jump down to this first example. Algebraically determine the y-intercept. You always find the y-intercept by setting x equal to 0. So that would be 0 plus 6 over 0 minus 3. And you get 6 over -3, which is -2. That's the y-intercept. Algebraically determine the x-intercept. The x-intercept is when y equals 0. this is y, essentially, right? So what x value will make this equal 0? What has to happen in a fraction in order for the fraction to equal 0? Say it again. So a 0 on the denominator? No, that would give an undefined. Say it again. That's still undefined. Just the numerator. 0 divided by anything will be 0 unless it's 0 divided by 0, in which case it's still an undefined. Okay? So if you want a fraction, the only way to get a fraction to equal 0 is if the numerator is a 0. So what would x have to be then? -6. Oh, that was written right there as a hint, in case you decided to read ahead. So then go to C, and it says, for what value of x is this function undefined? That's when your denominator equals 0, right? So what value of x will make our denominator equal 0? 3. And the reason, because when you divide by 0, you get undefined. And so the domain is pretty much always going to be all real numbers, with the exception of whatever numbers make your denominator 0. Wherever your vertical asymptotes are, really. So x can be all real numbers, except x cannot equal 3. Because 3 was that magic number from part C that made our denominator 0. So instead of all x's such that, I'm just going to do that. So I will show you the picture of this one and kind of show you how vertical asymptotes and horizontal asymptotes come to light. See how whenever things shoot off towards negative infinity and shoot up towards positive infinity, and you can kind of thread the gap there with a vertical line, that's a vertical asymptote. Our vertical asymptote on our parent graph is normally right here. It got shifted right 3 units because of that x minus 3. The denominator used to be x. Now it's x minus 3. Okay? And the horizontal asymptote normally threads the gap between right there, which looks like it's about at 1, because this does come above the x-axis. So I'm going to say it's like at 1-ish. Okay? You could look at your table of values, and you could keep going into the positives, and this is going to get closer and closer to 1 without ever actually reaching it. And that gives you sheds some light on what the horizontal asymptote is. Okay? So anytime you're asked, like in exercise 2 and 3, about values of x for which it's undefined, the domain of a function, this is always based on your denominator. You have to think about very heavily, your denominator cannot equal 0. So if we were to factor this, your numerator can't be touched, but your denominator can be factored into, let's guess and check. It has to be 2x and x to make 6. We would have 1 and 6 or 2 and 3. We want our middle to be 11. So if I put the 6 here, that'll give me 12 on the outer, and 1 here will give me 1 on the inner. So a positive 12 minus a 1 will give me the positive 11 that I want. So what x values will make this denominator 0? Lucas Bowen, give me one. Give me a value of x that will make the denominator of this function 0. look at your two factors. Focus on this one, and I'm just going to do that one because it's the easier of the two. Negative 6. Exactly. So negative 6 would make this thing undefined. And what's the other one, Mike? 1/2. It's like teeing up the denominator, though, right? Just like we teed up factors to find the roots last chapter. It's like teeing up your denominator to see what x really can't be. Depending on the way they phrase it. Find all values of x where they're undefined, negative 6.5. So, in exercise 3, similarly, your domain is always going to be that x can be any real number except whatever makes your denominator 0. So we're always kind of looking for the exceptions. So if I factor this denominator, has to be x and x, multiply to get negative 16, but I want my outer and inner to make negative 6. Owen, do you know what it is? Four times 2 doesn't make 16. 8 and what? Okay, which one's positive and which one's negative? And the 8 is? So that would give you negative 2x plus 8. What's negative 2 plus 8? Do you want it to be positive 6? So, what x values are not in my domain, Angie? What x values do I kind of exclude from my domain? Yeah, what x values? They kind of phrase them differently, but what x values would make this undefined? And? Very good. So 3 is your domain. X can be anything as long as it doesn't equal negative 2 and it doesn't equal 8. Now let me show you what happens on your calculator when you graph that kind of function. Because we have two things excluded, right? So you see 2 vertical asymptotes. One at negative 2 that kind of blocks that out, and one at positive 8 that blocks that out. Does everybody see that? Okay. All right. We're still writing inverses. This is a concept that's not going away. And this is a concept that this is probably the hardest type of function to do this in, where you switch the x's and the y's. We know our two-step process, and we solve for y. You're probably going to have to go back and re-watch this video and re-listen to this explanation that I'm about to give, because we're trying to solve for y, but y right now is locked up in the numerator and the denominator. It's not like we just have one of them that we can isolate, right? So it's a little bit trickier. You want to start by cross-multiplying, and when you cross-multiply, get your distribution done and over with. So xy minus 2x. And if I want to solve for y, then I have to get all my y's together on the same side of the equation. Get all your y terms on one side and all your non-y terms on the other. So I'm going to move this y term, xy, I'm going to subtract it over. Now normally you'd be lucky and you'd have like y minus 5y, and you could just make it negative 4y. You'd have y terms that had numbers in front of them instead of letters, so you would be able to just combine them. When you can't combine them, you want to just factor out a GCF of a y. That's how you'll get there to be only one y in the problem. If I divide a y out in front from both of these, I'll be left with 1 minus x. And now I can get y all by itself. I'm just going to divide the 1 minus x over. So there's my inverse, negative 2x over 1 minus x. If you're just factor out GCF of y. Okay, even and odd functions, algebraically, plug in negative x, see what you get. So if I plug in negative x, I'm going to get negative x squared minus 8 over 4 times negative x. And then I'm going to compare that to my original. Is it exactly the same? Is it the perfect opposite? Yes. And we kind of had one like this on our test because it was a fractional one on our test on Friday. If just the numerator or just the denominator is negated, then yes, it's a negated version. So this is odd. Hold on, we have 1 more minute. Cool it. The last section is just, it's been a while. Also, by the way, you could graph that and look to see if it's symmetrical with the origin or not. But when we have two functions, this is compositions, and it's been a while since we've done compositions. Alexa, can you take one and pass it around? But when you do f of g of negative 2, what is step 1? This was like first week of September, maybe second week stuff, but right, you work inside out. So we first want to find out what g of negative 2 is. So we're going to plug in negative 2 here. We get negative 8. And then we're going to do f of negative 8 and plug that negative 8 into the f function. And that will be our final answer. Once you get a homework sheet, you are obviously good to go. I'll have your test graded by tomorrow, I promise.